A very warm welcome to this, our first Be Curious event. Be Curious is a new, specially curated quarterly event programme for our external editors and editorial board members. Our goal in doing this is to bring together some of the finest minds in academia to debate the pressing issues of the day and, of course, the role research is playing in providing solutions. My name is Alison Mitchell. I have the privilege of leading our journals group here at Springer Nature and kicking off today's event. So I started my professional life as a researcher, but I moved very quickly on to publishing, and I've been in the publishing industry for over 25 years, starting as an editor with Nature, and then I was launched chief editor of Nature Review's Molecular Cell Biology. Like my colleagues here at Springer Nature, I'm committed to finding ways to open doors to discovery. And this new series, which we've developed specifically for you, our external editorial community, is a real celebration of intellectual curiosity. So we're lining up some wonderful speakers to stimulate questions and conversation about some of the big issues facing our planet. And I'm delighted to hand over to Ritu Dand, our Chief Scientific Officer, who's going to tell you more about today's speakers.
Thank you, Alison. It's my great pleasure to be here today to host our speakers. Like Alison, I also started my publishing career at Nature over 20 years ago, but not quite as many years ago as Alison. I was initially Nature's cancer editor and then the chief biological sciences editor. And in my current role, my focus is to champion editorial excellence across all our journals. It is an honour to be able to work closely with the editors to learn about their achievements and to support them to excel on their journals. Today, we're going to hear what it was like on the front line back in February 2020, when the COVID-19 first arrived in the UK, as well as how we will now move forward. I'm very excited to introduce our very special guest, and I will also take you through today's agenda. Our keynote speaker will be no stranger to most of you. Professor Sir Andrew Pollard is the director of the Oxford Vaccine Group at the University of Oxford. He's best known for his crucial role in the development of the Oxford-AstraZeneca coronavirus vaccine, and then leading the global clinical trials that allowed the first doses of the vaccine to be administered. It's an incredible achievement and a major milestone in the COVID-19 story. Andrew will be joined by Dr. Samantha Vanderslott, who leads the Vaccines and Society unit within the Oxford Vaccine Group. Her work focuses on public health and society, and today she's going to talk to us about vaccine hesitancy, which is also a major threat to a successful vaccination strategy. I'm not sure this area gets the recognition it deserves. After all, there's little point in creating a vaccine if the public refuse to be vaccinated. At the start of the global pandemic, we had a successful vaccine, but needed rapid and high-level vaccine uptake. It was a time when public confidence was at an all-time low and a fear of the unknown at an all-time high. And I look forward to hearing how people were reassured at that time to enable the vaccine rollout that we had. We will then be joined by our panel members who will continue the discussion. Firstly, Professor Gulsar Gabriel from the Leibniz Institute of Virology, whose own research focuses on the influenza virus and who is also on the editorial board of medical microbiology and immunology, as well as emerging microbes and infections. Gulsar will be joined by Professor Maria Alonso from the University of Santiago de Compostela, whose own research involves the development of nanovaccines for viruses such as HIV and nanotherapy for COVID-19. She is also the editor-in-chief of Drug Delivery and Translational Research. The panel discussion will be followed by a wider conversation with our audience and with an opportunity for questions. Before we get started, a couple of brief housekeeping notes. You do need to be logged in if you want to ask a question, and you can still log in now by clicking on the login button to the right of your screen. And to ask a question, use the Q&A function to the right of your screen. All questions will be taken at the end of the panel discussion, and the session is being recorded. So let's start this talk. The global pandemic has touched each and every one of us in some way, and some more than others. I vividly remember the 7th of January 2020, when Nature received that infamous paper describing what the coronavirus DNA looked like. Researchers in China had sequenced a single patient who worked at the market in Wuhan and who was exhibiting severe respiratory disease. This research paper provided us with the first DNA confirmation of the similarity of this virus with SARS and reinforced the severity of the situation. Nature had agreed to ensure all COVID-19 data was immediately released. And it seems from your first slide, Andy, that set the wheels in motion for you and your colleagues.
Yes, so as you said, the sequence of the virus was first available around the 10th, 11th of January. And we received that sequence here in Oxford on the 11th of January. And it's interesting to reflect back that that's the same day that the first death was reported around the world from COVID-19. Interestingly, an article in the New York Times on that day said we shouldn't worry because there's no evidence that the virus transmits between people. Of course, it's turned out that that very much wasn't the case. And what happened here in Oxford at that time was really before we knew there was a pandemic, the work went to design a vaccine really for interest because of the potential for a coronavirus to spread. And it was only a few weeks later, as cases started to spread around the world, that the accelerated work went to start testing in animals and manufacturing.
Andy, are you still there?
I am still here, yes. Do you want me to continue? I thought you might be going to ask another question, but that's fine. So then what's happened in the development after that was that after the vaccine had been manufactured, the clinical trials could then get underway, which started in April of 2020. It took a few months to make the first batches of vaccine and to test their quality so that clinical trials could be undertaken. And those initial trials run here in England show very good immune responses with the vaccine, so that those data could then be presented to regulators to move forwards to the very large scale efficacy trials, which were set up across the UK, Brazil and South Africa to demonstrate that the vaccine was able to prevent coronavirus infection. And that was a randomization between individuals who received the vaccine and those who had a control vaccine, which had no impact on coronavirus. And the way those trials work is that we wait for cases to accumulate in the clinical trials. The regulators required somewhere around 100 cases to 120 to accumulate, so that you can then break the code and find out what the efficacy of the vaccine looks like. And with those first results that were available in an interim analysis in November of 2020, we could then prepare all of the data for submission to regulators. And the first approval then came in the end of December here in the UK in 2020. So the clinical trials took about 7 months, about a month of regulatory approval, giving a whole development timeline of about 11 months. Now, in some ways, that seems really fast. But actually, there were many reasons why that was possible. The first being that we actually already knew how to make coronavirus vaccines. Because of the emergence of previous coronaviruses, SARS 20 years ago, MERS about 10 years ago, there's been a huge amount of work on coronavirus vaccines that told us that the spike protein of these viruses was the key antigenic target of a vaccine development. And so from the sequence, it had been possible to identify the spike protein gene, and that was what was then used for all the developers to make coronavirus vaccine. So all that complex R&D work, 20 years of work had already happened for coronaviruses. So there wasn't that really difficult step to undertake. And secondly, we had these amazing platforms, the viral vectors like the ones we used in Oxford, the RNA vaccines that Moderna and Pfizer have used, which have more than a decade of experience of their use and testing for both platforms. And that meant that having got all of that knowledge, bringing together the knowledge about coronaviruses, the platform technologies, we could go straight into that manufacturing and clinical development phase, which allowed the trials to run so efficiently during 2020. Normally, when we run trials, we have lots of gaps between the phases because we wait for funders to be persuaded to fund the next step. One of the great things about, in some ways for the pandemic was that once we got underway and the data were looking good, the funding from governments mostly was available. So we didn't have those often years of delay waiting for the next stages of development to be funded, which allowed things to progress really quickly in 2020. And lastly, I think the other really important accelerated bit was that manufacturing was scaled up at huge financial risk before anyone knew that these vaccines actually were going to work in humans. And normally manufacturers don't do that scale up until they're pretty sure because it's so expensive. But it is also one of the areas where vaccines get stuck, is they're complex biological materials which can be very difficult to scale. And so that effort that happened in 2020 meant that when the launch was ready for our vaccine in January of 2021, or for Pfizer just at the end of 2020, there were already large numbers of doses had been prepared for that rollout. Perhaps I'll stop there and hand back to you, Ritu.
Thanks, and it's absolutely phenomenal. It really is on how you were able to achieve so much so quickly during a global lockdown, I should also add. So where are we now with COVID-19? People are still getting infections. Are we going to be stuck in a cycle of infections? Will the pandemic ever end?
Well, it's a really good question. And I think the thing that is certainly people are rehearsing all the time at the moment. But I think the really important question is, where are we in the pandemic? And this slide, which is up now, sorry, you've gone too far. Go back one, please. The slide that's up now shows the first two waves of coronavirus that happened here in the UK. The first with the original virus, and then the second big wave with the alpha virus. And what we're seeing is the number of deaths in the UK with those two waves. And if you take death, which also corresponds to critical illness with coronavirus, and that's what was causing the pressure on the global health systems. Essentially, once the vaccine rollout was underway, in the early part of 2021, the pandemic ended, if the pandemic is measured in terms of death and critical illness. And you can see here on this slide that where the blue arrow is, which is when the rollout was established, that essentially the number of deaths fell to a very low number in comparison with those previous waves, because the vaccines are fantastically effective at preventing severe disease and death. And indeed, even those smaller peaks after Delta and Omicron arrived, many of those cases are deaths which are people who died from other causes, but at the same time as they had recently been infected with COVID-19. So some of those are deaths of people who are in car accidents or fell off a ladder. And this is an important feature of the quality of data that we're able to get when you look at a lot of the data sets which are put out in the public. We can't actually pull out exactly which of these cases is caused by severe coronavirus and which is caused by other things. And indeed, if you look today, to come to your point about where we are now, we really are not seeing large numbers of people in hospital with that nasty illness that we saw in 2020 with severe breathing problems and severe infection in the lower respiratory tract. Now we're dealing much more with people with frailties and comorbidities, particularly the very elderly, who have worsening of their status as a result of a much milder infection than we saw previously. So, for example, if you have heart failure and you develop flu or COVID, you're much more likely to end up in hospital than if you don't have those viruses. And so what we're calling severe disease today is much more a combination of an underlying health condition or frailty with coronavirus, rather than direct damage of the lungs by the virus itself, which was the big problem in those previous huge waves of mortality. So what of the future? Well, I think it's very likely with such a transmissible virus that it will continue to develop new variants and transmit in human populations for the rest of our lives. And the likelihood is that that transmission will look much more like flu does, which comes in a wave each season, each winter, rather than having the very many waves that we've seen over the last couple of years. But I think we should be prepared for the impact of this virus on our vulnerable populations each time it does arrive. So it's not as if coronavirus is no longer a problem, because it is. It's just it's not the scale of a problem that we saw in the earlier part of the pandemic.
And I believe that graph is of the UK. Is what's happening globally? Have vaccines had a similar impact around the world?
Well, in most countries, we've got a similar pattern of high levels of vaccination or previous infection, and that means that much of the world today looks rather like here in the UK. Because, of course, infection also drives immunity. The problem with infection is that if you have infection in an unvaccinated population, some of those individuals will die. But there are some countries which have managed lockdowns over very long periods of time without getting high coverage of vaccination in their population. And we're seeing this in China at the moment, where there's been the initial policy was really to target vaccination in younger age groups, which meant that the really vulnerable older adults for coronavirus were not immune. So the risk in that situation, if you don't use lockdowns to immunize those who are at greatest risk, that when the virus finally does arrive, that essentially your pandemic starts at that point. So the real challenge for countries which have got low levels of vaccine uptake and no previous immunity from the virus, from infections today, is if they don't vaccinate, they're going to see the high mortality that was seen in other parts of the world. They'll get it later. And I think this is the real challenge in China at the moment, is to get higher coverage in the elderly as the virus starts to spread. And this slide we see here just shows the amazing global impact of vaccines, with almost 20 million deaths averted last year from the global vaccine program.
Thanks, Andy. That's been a fascinating insight, and I'm sure there'll be more questions later. But for now, I'd like to bring in Samantha, because it's all well and good having a fantastic vaccine, but we need to get that vaccine into people's arms, as human beings aren't always the most compliant. So Sam, what was the mood when it came to vaccine rollout back in 2020? 21, actually, when the rollout happened.
Thanks, Rita. So I'm sure we all remember globally there was this huge amount of anticipation and public and media interest in COVID-19 vaccines even before the rollout. So clearly there was this very high demand in some sections of the population and maybe a bit lower in others. And then we add to that not everyone has this equitable access to vaccines, even if they wanted it. So whether that's on a national basis or with more simple practical steps to make vaccination as easy as possible. That's something that we should always consider about vaccine hesitancy. Are we making it as easy as possible for people to vaccinate? So I think there's the social acceptance, the politics, the economics and public policy aspects of vaccination to consider. And this comes really hand in hand with the scientific development. We're seeing this in China right now. And I think as Andy hinted at, that's worth digging into a bit further. So, of course, we see the anti-lockdown protests that have been in the news. We also know that one of the key groups, the elderly, has a lower rate of vaccination. Unfortunately, they're also the group that has the highest risk from serious illness and even death from COVID. And they're reluctant for quite a number of reasons, and that's been influenced by public policy and also government messaging. So firstly, testing out China's vaccine on a younger population and saying there wasn't enough data to begin with. That did mean that the elderly weren't targeted as a group to be vaccinated. And also China prioritized the working adults in their rollout. So the elderly didn't come first in the queue as we saw in other countries. Other points to consider in terms of public health are the community infrastructure to actually administer the vaccines, and that maybe is lacking in targeting the elderly and also addressing their very specific concerns. So this group have been worried about underlying health issues and whether that affects their ability to vaccinate. So I think that this good comms and engagement in vaccination can really translate into lives saved. And it's why we need investment in times and also resources into this. I also think when governments tend to get really worried is when we can't reach some groups for vaccination and where there's resistance and really outright opposition. So this is the vaccine hesitancy, but maybe what gets labelled as the anti-vaxxers. And there's a particular fear that as that group grows in strength and in numbers, that they can influence others. And in worst case scenarios, they might break down vaccination programs completely. And so I think you can see in this slide being shown that there's a banner being held up, and those showing opposition to COVID-19 health measures also include vaccination in that. So they're connected, but also making a connection to misinformation and conspiracy theories. A popular one that has been going around is that 5G mobile technology can influence your immune system and weakens it. So that was a previous conspiracy theory. Unfortunately, those types of conspiracy theories are more popular in times of uncertainty and when the trust in institutions are particularly weak. And this is quite a challenging situation to deal with, and unfortunately is quite likely in times of pandemic.
So what is an ideal sort of rollout strategy for you, given all the things that you've seen globally?
Well, I think the tendency has been for governments to resort to more coercive policies to go in line with rollout. So when they see a lower uptake, there's a temptation to introduce vaccine mandates. And so this is requiring people to be vaccinated as part of the law, or to keep their job, or to access public benefits. An example has been in France, so the pass sanitaire, or a similar policy in Italy also. And this has been requiring over 12s to present vaccination as proof that they could access public spaces. And we did see quite a positive uptake in vaccination because of that policy, but there are downsides that we really need to consider as well. So you can see here there's a graph shown by some colleagues that show the impact upon attitudes. And that's been increasing feelings of doubt and anger towards COVID-19 vaccination after the pass sanitaire was announced and then eventually implemented. So this mandatory vaccination can also make people more vaccine hesitant, more generally, and less willing to be vaccinated voluntarily. I think also what was interesting from this study was that they found we may not be reaching the groups that we really are most concerned about. So, for example, the elderly again, and people from lower socially economic groups. And they're the ones that are most adversely affected by COVID a lot of the time. But it might be harder to get them on board for these types of policy if they're less technologically literate, or if they're less inclined to want to join public spaces. So I think the temptation is that mandatory vaccination offers what seems like a quick and inexpensive fix to the problem of low vaccine uptake, but as I've argued, that can increase hesitancy and miss out key groups.
Yeah, and as we heard from Andy, COVID's not gone away. The death rates may be lower. We still have long COVID. How do we ensure that the vaccine remains socialized, given that it does seem there will be a need for annual vaccinations?
Yeah, good question. I think there are two key areas that I think really need to have more attention, and that's in community action and social media and online presence. And we can see on this picture on the screen that displays a community champion in the UK, and she's videoing herself getting the COVID-19 vaccine. And so in the UK, there was a government policy to fund local community groups to promote vaccination. Some of the groups were missing out from government messaging. They didn't feel like the messages were particularly relatable or tailored to them. So we really need people on the ground providing information, answering questions and concerns, and giving reassurance and also advice. And then so the other area is social media and online presence, which I think people are increasingly turning to as a source of information. But of course, that can be dangerous. There are quite low barriers to entry to publish online compared with traditional media. So we end up having this echo chamber on social media with like-minded people in the same ideological orientation sticking together. And that really does lead to a polarization in user opinions online on platforms like Facebook. Also, it's an area where health authorities have shied away from in the past. We saw quite quickly with the COVID-19 pandemic that that quickly became an infodemic of misinformation and fake news. And if that very reliable content isn't there, then the void will be filled by someone else. And I think what governments and health authorities need to recognise is that there will be uncertainty, and that's better to state rather than to avoid. And then lastly, I think more could be done really to counter misinformation. For example, with fact-checking organisations and also supporting civil society groups who are actively pro-vaccination.
And is there anything else that you think we should be doing to be prepared for future pandemics?
So from my perspective, I have to say that this work of public communication engagement and also investing in immunisation services and social science research on this topic, that needs to happen outside of the outbreak and pandemic situation in peacetime instead of leading to a reactive response.
Yeah, absolutely. Thank you, Sam and Andy, for those fascinating insights. I'm going to move us along to our panel, who are itching to ask a question. Khalsa, is there anything you would like to add to this discussion?
Oh, yes, absolutely. So thank you also from my side, Andrew and Samantha, for these insights. As you've already highlighted, that the course of a pandemic is multifactorial with many scientific and non-scientific challenges we are faced with. Vaccination during the pandemic has clearly affected the course of the pandemic, as we just heard, resulting in many millions of lives saved. Still, I think challenges posed by the pandemic with regard to vaccination might not be over yet. Indeed, some aspects might have just started with respect to upcoming complex epidemics. So one of these challenges is that circulating SARS-CoV-2 strains will likely collide, as we see at the moment, with other co-circulating respiratory viruses that show seasonality, such as influenza, such as RSV, which both of them, pose a significant disease burden on their own already. So this so-called triple epidemic, and we are all experiencing this at the moment, might cause a considerable disease burden, in particular for high-risk groups, such as people with underlying medical conditions, and further continue challenging existing healthcare systems on top. So I am curious to hear your thoughts, Andrew, on how the future of vaccines and vaccination strategies should look like, in your opinion, against seasonal respiratory virus infections in order to continue the vaccination success also for upcoming, not always very predictable respiratory epidemics.
Thanks for the great question. I think one of the really interesting issues that we're facing for today with these respiratory viruses is that it's actually a similar problem for all three of the viruses you've mentioned, in that we're dealing with a population that already has some immunity. Most of us got immunity to COVID. We've all got immunity already to RSV, and we've all got some immunity to influenza. And yet we still, throughout our lives, get reinfected with these strains. And we've become very aware of that with COVID, but of course, every few years, every one of us will have an influenza infection and certainly an RSV infection as well. And so the question is, how do you improve immunity in those frail individuals in the population so that we keep them out of hospital? And it's a much bigger challenge, actually, than the one of making a vaccine in the pandemic, where we were trying to stop severe disease as the most important thing to do. We're able to do that already with the immunity that we have. But the challenge here is to prevent infection, which, as we've seen with COVID, even with vaccines, is quite difficult. It's difficult with flu to each season to have a vaccine very well matched to the virus that turns up so that we prevent infection. And I think this is going to be the real problem in the future, is vaccines that are well matched to the circulating strains of COVID and flu to prevent infection completely, rather than the much easier task of just preventing severe lower respiratory disease, as we saw in a naive population in the pandemic. But how that can be approached is that the technologies are now advancing towards the possibility of making combination vaccines that cover all three viruses. And I think in future, and I can't tell you when that will be, we may well be looking at a winter seasonal vaccine that covers several flu strains, perhaps several COVID strains, as well as RSV. And if that is able to reduce the infection burden in those vulnerable individuals in the population, that'll have a huge impact on our health systems. And it is an exciting moment. We've got COVID vaccines that do work. We've got influenza vaccines which work. And for RSV, there are recent reports in adults as well as in pregnant women of new vaccines which have substantial efficacy against RSV, at least in the short term. So that means that if we are able to work out how to assemble those as combinations, we could have a winter seasonal vaccine that prevents these three viruses from causing severe infection. Now, the big challenge there is predicting which variants are going to be there in the winter. Today, many countries are vaccinating with a bivalent COVID vaccine covering an Omicron variant plus the original COVID strain. And the problem with that is that many of those vaccines are actually covering variants that are no longer circulating. So, for example, one of the vaccines being used in the UK covers BA1 and 2. And that's the last variant we had, not the new one. And this is the difficulty, is that as with flu, we're going to have to get a good system in place to predict which viruses are going to be coming in our winter. And the way for flu that's done is the data are looked at from other hemispheres to try to give a best prediction of which flu viruses might then come in our winter. As far as the technology is concerned, for example, the RNA vaccines have a relatively high possibility of combining the RNA sequences from different viral strains to make a combination vaccine. And at least in theory, that is a possibility of a way that we could cover RSV, COVID, and flu relatively easily in future winters. And the only other challenge, of course, for COVID is so far it's not proven itself to be a definite winter virus. We've had it in the summer and in the spring as well. So timing of when you might put together a combination vaccine is much more difficult. But I suspect that these viruses will settle down into a more predictable pattern again in the future. that they really hadn't been showing during the course of the pandemic. Of course, there's been no flu for 2 years, and now we've got quite a substantial season. We missed a year of RSV, but then we had a very long season last year, and we've already had a very long season this year. So they've not been quite as predictable because they've been unsettled by the pandemic lockdowns. But the future, I think, we may get into a position where we could logically plan a pre-winter vaccine program that covers all three.
Thanks, Andy. That would be wonderful if we can. Welcome, Maria. I'm just going to ask the audience. Remember, Maria's going to put her question to the panel, but after that, we're going to have questions from the audience. So if you do have a question, please get writing now. We'll be able to take them straight after Maria. What's your question then, Maria?
Okay, so first of all, hello to everyone, and thank you to Samantha and Andrew for, sharing with us your experience and your knowledge. It has been great listening to you. So as my background is more on vaccine formulation, I have a different kind of questions, I have to say that scientifically speaking, the time of the pandemic was probably the most challenging experience for me in my research activity, working on nano delivery carriers for vaccines. And that, as Andrew highlighted, the way we were doing, and we continue doing actually, research was a little different as compared to what we did in the past, in the sense that we had to try so many different approaches at once without knowing which of them was going to make the way. That was kind of an inflection for us doing research. But besides my work, which is mainly on RNA vaccines, I guess the question I have for Andrew is that what kind of lesson have we learned that can be useful for the continuation of COVID and other viral diseases from the, let's say, from the, I wouldn't say vaccine formulation, but, if we compare RNA vaccines, which make use of, lipid nanoparticles as compared to viral vaccines, what have we learned in terms of their possibility to be used for, any kind of viral diseases for preventing? What is the potential of both kinds of vaccines, and how you see the future? Some people have been saying, we don't know what is going to happen after, 10 or even more doses, administrations of these vaccines. Do you see a difference in the future on how viral vaccines will perform versus RNA lipid nanoparticles or other or protein vaccines? How do you see the future of these different types of vaccines?
Well, I think that you raise a very important issue, is how would the different types of platform technologies be used in the future? One of the things at this moment, I would say, is that we need access to all of the different technologies. If there was another pandemic tomorrow, we'll be in exactly the same situation. To get the global scale that we need to protect people, we need the different technologies. There's also a scientific reason for that as well, which is that we don't yet know whether either a viral vector or an RNA vaccine will be the solution for every potential pathogen. If we have a virus that we know nothing about, it might be that the inactivated vaccines, like those that were produced at huge scale in China, is the only way that we can logically put together a vaccine that will provide at least initial protection until we've done that research to work out exactly which part of the virus is critical for protection. Similarly, if some bacterial proteins clearly wouldn't normally be expressed through mammalian cells, and so if it was a pandemic of a bacterial disease, as happened, of course, with the plague in the Middle Ages, then it might be that these are not the right types of vaccines to use. That maybe for those we need to use more traditional conventional approaches in protein production or with whole cell bacterial vaccines. So I think it's important, first of all, to say that we need to make sure we don't throw out all the old technologies, because they may be absolutely critical for the future. I think, I'm not sure whether you were getting at, the great thing about RNA is that it's much closer in its production to a biochemical process. And that means that it's much easier to standardize and to regulate and also to manufacture more quickly. So there are huge advantages of RNA technologies, even in their early days as they are today. And I think we can anticipate with further development, with further advantages in the thermal stability, perhaps addressing optimization of the nanoparticle itself. That we're at the start of an evolution of those vaccines, which make them incredibly powerful tools for the future. I think it's an exciting time for vaccines in that we've got so many approaches that we can use. But fundamentally, if we're talking about future pandemics, we at the moment we are in the dark about the science behind most viral and bacterial pathogens in the way that we weren't with coronavirus. We were so lucky to be threatened with a virus that had already had all of that work done in the past. So we need work on the viruses more than we do on the platforms at this moment, I think.
Thank you, Maria. Thank you, Andy, and thank you, Gulsa. So I'm going to close the panel discussion now, because we have lots of questions coming in, and anyone is welcome to respond. One of the first question that I can see is, I wonder why one still gets sick when already vaccinated. With many other vaccines, one does not get sick. Does somebody want to start with that one?
Well, I'm happy to speak to that. So the difficulty is that we really do not have a good understanding of how to induce sterilizing immunity on the mucosal surface in the upper airway. And when we look at infections with influenza, the vaccines do not provide completely sterilizing immunity, the same with COVID vaccines. And the reason for that is that you need extraordinarily high levels of antibodies in order to block infection. And our immune system doesn't seem to sustain those very high levels for a long period of time. So that's the first problem. And the second one is that these viruses keep throwing up new variants, which even if we did have high levels of antibody, escape from those high levels of antibody. So the reason why we're getting repeatedly infected and feeling unwell is because of the duration of immunity that's required to provide sterilizing immunity on the mucosa is short, and the new variants emerge. Now, that doesn't mean that we're losing immunity. All of us who have been vaccinated or have met the virus have astonishingly loads of immunity. It's just still not enough for these viruses. And that, of course, is why many respiratory viruses are so successful, is that they cause infections in our childhood, and they continue to cause infections through the rest of our adult lives. The human coronaviruses, which many of us will have had repeatedly through our lives, we got our first infections as children, but we still get repeatedly infected every 4 or 5 years as adults. So none of this is so surprising. It's just the problem of RNA viruses, which make lots of mistakes when they're replicating, and every now and then they throw up a new variant which spreads well and keeps us on our toes.
Thanks, Andy. Question number 2, what do you suggest for the people for whom the vaccinations are not effective, e.g. those that may be immunocompromised?
Well, immunocompromised is a very broad category. And of course, there are some immunocompromised individuals who can respond perfectly well to vaccines. But if we narrow it to those who really don't make efficient immune responses and remain as if they've never been vaccinated, so they're very vulnerable to the severe consequences of COVID. And I think the best option for them are monoclonal antibodies, which have an extended half-life and can prevent infection. But the challenge with those is they tend to be variant specific. So as new variants emerge, you would need to have a new monoclonal developed for that new variant, which over time is quite an expensive approach. The only other alternative is antiviral drugs, of which we have some available at the moment for COVID. So those are the two approaches that are available. And I think we need to better identify who are the risk groups for monoclonals and those drugs, so that we don't use them on a very large scale and perhaps drive increasing resistance by doing so.
Thank you. What are the reasons for long COVID? Any genius know the answer to this one?
Well, I don't know the answer, but I mean, I think it's worth saying that long COVID is a terrible description of a large number of different conditions. And so really we have to better define what we mean by it in order to understand what its causes are and then what the appropriate treatments are for it. But there's clearly some individuals who have an inflammatory condition after they've had COVID, and that inflammation can cause very significant problems with different organ systems. There are some people who have sort of a more like a chronic fatigue syndrome after COVID, which recovers with rehabilitation and time. And of course, many people have a combination of different features. But I think in terms of understanding long COVID, there's a lot more research to be done.
Impressive program by the Jenner, an impressive impact on lives saved. What were the challenges of setting up the objective impact assessment data as one involved in vaccine impact assessment? What are the other indicators you used?
I'm not quite sure I fully understand the question about what indicators are being got at, but I think the clinical trial part of it is very clear that you're working with regulators to define a level of efficacy that meets those standards for approval. And in the case of COVID vaccines, the regulators set an efficacy of a minimum of 50%, and the lower bound of the confidence interval around that should be somewhere above 30%, and some regulators said 20%. So you've got a relatively tight range of the point estimate and the confidence intervals for efficacy, and that means that when trials are conducted, you have some confidence that the uncertainty there always is in a clinical trial is dealt with by having a lower bound of the confidence interval that's high enough. If you set it at 0, then of course the real point estimate might be 0. So there's that's the reason for having it above 0. And in terms of impact after implementation, and then I think the evidence of reduced deaths and critical illness hospitalizations is the type of evidence that is being looked at using observational studies. The difficulty with those is they're incredibly at risk of bias, because the way that we use vaccines means that it's very difficult to control or find a control group. For example, in the UK, it's almost impossible to find a control group of unvaccinated elderly patients because nearly everyone was vaccinated. And so when you're trying to then work out how well a vaccine works after the rollout of the vaccine, you don't have an equivalent control group of people in the right age group to estimate exactly how well the vaccine is working in that age group. You end up with a control group of younger people. So I think there's some real challenges in the observational effectiveness studies that you can't get around, which is why the efficacy of the trials where they're randomized are so important. I'm not sure if that answers the question.
I think it did a very good job. I think this is going to be the last question. Do we know enough about the long-term side effects of repeat mRNA vaccinations?
Shall I take that one as well? No one else seems to be putting their hands up.
Well, I will, after you've answered, Andy, I'll ask Maria if she has anything else to add, because I'm aware she worked on those.
I think the answer is that certainly most side effects of vaccines happens relatively soon after vaccination, and we know that looking back over the whole history of vaccination. And so we've got a very good understanding of the types of impacts we see, the very rare side effects we see from vaccines. And I don't think there's any reason to think the RNA vaccines are any different from that. We know we've got some associations, for example, with rare events such as myocarditis, which happen particularly with second doses in the initial rollout. But I think it's true that perhaps Maria was referring to this when she brought it up, that we don't know what happens if you've had 10 doses of an RNA vaccine, and all of that has to be monitored. But there's no reason to think that there should be a specific problem from the data that we have at the moment. But like all drugs and vaccines, there needs to be good surveillance systems in place. I think one of the things I find reassuring is that our regulatory system today, particularly with the access to electronic data from health records, makes it much easier to spot signals of side effects in the data and then to be able to react appropriately if they happen. But as I say, we've got a perhaps more understanding of COVID vaccines than we've had ever before of any vaccine, because the systems are so much better today than they were even 10 years ago.
Thank you, Andy. Maria, is there anything you'd like to add to that?
Well, I do believe that everything has been said, but I could probably add in terms of the lipid nanoparticles that have been used for delivering RNA vaccines, they seem to be, the information we have until now is that they have been very safe. And we have to keep in mind that some similar compositions are using for the delivery of drugs much more frequently. So when we think about vaccines, we think about administering one dose, or different doses, very separated. So not many, it's not like chronic treatments or something like that. So I don't think we should expect high toxicity from the particles carrying the RNA. In principle, all the components are very well known. Maybe the condensing lipid is the one that but at this point already quite well known. So as I said, given the limited number of doses that we are going to give, I don't think we should expect toxicity from the carrier itself, and from the RNA, it seems that it could be probably the same. So I am quite optimistic. However, I do have a question again for Andrew in the sense of the efficacy. We already have information about the efficacy of the different doses that we have been administering. Obviously, we have been dealing with different versions of the virus. So do you think that the immunity that we are building is going to be stronger and stronger with the different doses, or lower and lower, or it will be, pretty much the same after every single dose? Do you think that the fact that we are administering, different doses, consecutive doses, is going to change the immune response in one way or another?
It's a good question, and one of the real challenges in answering the question is that we're in such a different situation from before. When we started using these vaccines, as in the clinical trials, we were comparing a group who had been vaccinated with a group of individuals who'd been neither infected nor vaccinated, and so you get the absolute efficacy of the vaccines from those studies against whatever endpoint. And of course, one of the problems in comparing the trials is they use different endpoints for what was severe disease and mild disease. So you can't compare different trials, but within an individual trial, you get an absolute efficacy of the vaccine. The problem in doing a study today on efficacy or effectiveness in the rollout is you're doing relative effectiveness, because you're comparing people you vaccinate with people who are already immune from infection and vaccination. And so the actual number will always look much lower than it did before. So it's really challenging to answer your question. because your control group is no longer a completely naive group, and which is a good thing because most people have been vaccinated. But it's one of the reasons why we see relatively low efficacy of vaccines in preventing infection for these respiratory viruses. I don't think there's any reason to think that the immune system is going to give up on us with future doses. I certainly think that there is a potential for slightly lower immune responses in people who already have a lot of immunity, because there is a negative feedback in the immune system which says if you've got very high levels, that you don't want all your lymphoid tissue fighting to make even more. And so there is a bit of a negative feedback. And we see that in flu. If you've had the flu vaccine last year, then your immune responses are a bit lower this year because you've already got some residual immunity from last year. But you're still better off to be vaccinated than not vaccinated. Mm-hmm. And I think that's likely to be how things will turn out with COVID in the future, that the apparent rise in antibody may be a bit less because we've already got some antibody. But it's still going to, in terms of protection, going to be better than not to be vaccinated.
Thank you, Andy. I want to move us on to the final segment of the seminar. Thank you to Andrew and Samantha, our keynote speakers, and as well as our panel, Maria and Gulsa. Thank you very much for making the time. And I'm now going to hand over to Alison to give us some final comments before we call it a wrap. Thank you very much.
Thanks, Ritu. And I'd just like to add my thanks to Andy and Sam for fascinating insights into one of the most significant scientific challenges of recent times. And of course, to Maria and Gulsa for kicking off the thoughtful discussion. We will be following up after today's event with a short survey. So please do consider, if you can, filling that out and letting us know what you think of today's event. So as I mentioned earlier, Be Curious has been created for you, for our academic partners. Your commitment to our journals, the support you give Springer Nature in helping us open doors to discovery is invaluable. So thank you very much for everything you do for our journals. At Springer Nature, we're committed to supporting ways to accelerate and amplify the communication of robust science around the world. So I'd just like to end the session today with a couple of highlights from our first report, which we published recently, to show the progress we've been making here. So as a result of our combined efforts, we've seen average citations to our journals increase 60% in 3 years. As a proxy for whether an article has been reused or not, these are numbers we can all be really proud of. It's not just the reuse of our research that we're seeing increased results with. So last year, over 2.6 million people interacted with our platforms every single day. And the number of times a piece of content, a piece of the wonderful research that we have the privilege of working with you to publish is downloaded has doubled from 2017 to 2020. We're also investing more in wider science communications to take research even further. So if you haven't yet signed up for the daily Nature briefing, I would highly recommend it. We now have 1.5 million people receiving this daily digest of science news, not just from Springer Nature, but news from across the whole publishing space. We're also acutely conscious of the need to improve how we keep you up to date with what's happening at Springer Nature. For example, information on our editorial policies or developments and updates on our publishing strategies. And so we've also launched the Spotlight on Editor webinar. And each month, there's a presentation from us on issues of interest to journal editors. So for example, recently we've run Spotlight Ons covering the UN Sustainable Development Goals, new editorial policies, and most recently, strategies to enhance journal impact. So please do look out for information on these events in the Editor Update newsletter or by subscribing to the Spotlight On channel. We're also launching a lot more training for our editors, from resources to support finding reviewers to help with navigating difficult decisions. And again, you should be able to find more information on this in your monthly Editor Update letter. Of course, there's always more to do. It's important that we continue to listen, to adapt our plans based on insight from the communities that we work with. And this is why you as editors will start to hear more from us than maybe you might have done in the past. And we really hope that we'll hear a lot more from you because we're certainly listening. So thank you very much for coming along today.